ago.
5 months ago, no, in May. Actually, in March. No, maybe May. All right.
It was actually 20 days.
Next topic we have to talk about is continuity. All the things that we are doing right now, all these limits, the continuity, they all come into play in the next chapter when we start getting into our derivatives. These are things that have to happen, so we need to know what they mean before we get there. So if you, I know you guys like to fact check me, so you go home and read your textbooks and make sure I don't tell you any lies.
Absolutely.
Right? That's what you do.
We do?
Yes.
Absolutely we do.
I thought you started
If you go and read your textbook from this, it is a much more in-depth scientific type explanation than we are going to go through. If you were to try to like look up an answer to one of these, their answers are going to look a little bit different than ours, because I'm wanting more that you can understand what continuity means than writing it in calculus type notation. Okay, so we need to know what this means as we move forward, and that is my focus on those.
Will us not learning how to write it in calculus notation hurt us in the future?
No.
Okay.
Not with this topic, which is why sometimes I make you do it in the correct notation, and sometimes I'm like, doesn't really matter. Because after Calc 1, they just assume you know this, and they don't ever make you show it again. So.
That's awesome.
All right, so continuity. We talked about being continuous back in college algebra, pre-calculus, and we said if something is continuous, that means you can graph it without picking up your pencil, essentially. We have a better definition now, a little more precise. Continuous has to do with the limits. So if we look at this, it says the limit of a function as x approaches a can often be found simply by calculating the value of a function at a. Functions with this property are called continuous. So we have seen with our limit laws, sometimes we're allowed to just plug in the number. When are we allowed to plug in the number?
When the denominator went to polynomial. And then
If it's a polynomial, and if you think about the graph of a polynomial, those are always just nice smooth curves, right? Would you agree that they are continuous everywhere?
yes.
Yes, and so therefore the definition adds up. We can just plug in the number because the graph is continuous everywhere. If we look at radicals, as long as you are dealing with a part of the domain that's defined, then we can plug it in. And if you think about like the square root graph, is it continuous when we graph it? Yeah. When else are we allowed to just plug in?
Function or fractions as long as the denominator is not 0.
Okay. If you think about those rational functions, when we graph them, where do they get asymptotes?
Anywhere.
When the denominator is 0. So as long as the denominator isn't 0, is the graph continuous?
Oh, yeah.
Yes. So all of this comes back to being continuous, all those limit laws. There are really 3 requirements for continuity. This is the important slide. This is what you need to know when it comes time for our test. You need to know. In order for a function to be continuous, these things must happen. The function has to be defined. Okay, so it has to be a part of the domain. The limit has to exist, and those 2 things have to be equal. So in order to say something is continuous, the function has to be defined, the limit has to exist, and they have to be equal to one another. That's what we will be verifying every single time we're talking about this. The next slide is just talking about what I've already mentioned. Geometrically, we said if it's continuous, you don't have to pick up your pencil. So if it's a place where you would pick up your pencil, that's called a discontinuity or a break in your graph. So if I tell you, identify the discontinuity, you're just telling me where is our graph not continuous? Where do we pick up our pencil if we're graphing it? So in this one, if I ask where is this graph discontinuous, where do we have a break in the graph? I is that the only one? 5, anywhere else? 1. When I ask for the y, I don't want the algebra explanation of you pick up your pencil. I want you to use the rules of continuity. So 3 things have to happen. The function has to exist, the limit has to exist, they have to be equal. So when I'm asking why, I want to know which rule did it break. So at 3, does the function exist at 3? Do we have a closed circle somewhere at 3?
Yes.
Yes. Does the limit exist at 3? No. So you can just say limit does not exist. Alright, at 5. Okay, does the function exist at 5? Do we have a point on our graph when x is 5? Yes. Does the limit exist at 5? Yes. If you're coming in from both the left and right, they go to the same place. Are those values equal? No. So, you could say the limit is not equal to the function. Or you can use, if you want to use proper notation, you could say the limit as x approaches 5 of f of x is not equal to f of 5. You know, I don't care if you want proper notation or not. You can tell me a limit doesn't exist, the limit does not equal the function, that's fine. That's enough for me to know you looked at your laws. At x equals 1, does the function exist?
No.
No. The function does not exist because there is no point on my graph when x is 1. So that kind of illustrated all 3 rules that could be broken. Do you guys understand each of those?
So the function existing is because there's that point, the closed circle.
Yep.
Now I understand.
Okay, if I ask you to look at the graph of f of x equals 1 over x minus 2.
X can't be 2.
X can't be 2. What happens when x is 2? I mean, we could go back through our whole like college algebra spiel of what these look like. Remember the rules for like horizontal, vertical, and oblique asymptotes and all that.
What is oblique is a
Oh, I'm locked in.
This one would have a horizontal asymptote of.
2.
You all fail.
1/2
No.
was.
No.
0.
Yes.
Yay!
I don't know why though.
It's anytime the degree on top was smaller.
Oh.
It was 0. So if you graphed it on your calculator, if you plugged in points, if you remembered your college algebra rules, ooh, that was crooked. It looks something like this.
What is the horizontal asymptote being 0 different? That's not
It
right.
just tells us where the graph breaks horizontally. It breaks over
Oh,
the axis.
I'm thinking
So why do we know that it looks like that? Because we just know.
Because it's
'Cause
never
we're
going
that
to be bigger than 1. How?
Yeah, you could graph it on your calculator. You could plug in points. You could do a lot of things.
But that's because the top is less than the bottom.
Yeah, come on.
Whenever I saw that 3D
It's like the parent function of 1 over x. Remember that reciprocal function? Shifted right to. Come on, Sam had it. Like the rest of you are just failures.
What picture are you seeing in your head?
It's a 3-dimensional, it's color coded, it's
Yeah.
it's intense.
I don't know.
Yeah.
Where is this at?
In her head.
Is
Well,
it,
She just knows
is
these
it real?
things.
Yeah.
Where did you see it at one point, or did you?
I taught you this. That's where you saw it.
Oh, okay.
Okay.
Sam had me really confused.
I'm actually
So.
thinking in 4 dimensions.
Where is this? Is this graph continuous everywhere?
Not everywhere.
Oh.
Where is it not?
2 and 0.
You give me the x value. So at x equals 2. At x equals 0, it's still continuous. What's the reason?
Your asymptote, the function does not exist.
You could tell me the function does not exist. You could also say, does the limit exist there?
No.
No. So I would accept either explanation. The function isn't defined at 2 and the limit doesn't exist at 2. Alright. You wouldn't have to give me both reasons, just one is sufficient. Alright, let's look at another one.
Oh my gosh, I'm seeing it.
line.
It's a line.
Oh, wait.
Two lines.
It's
Ooh.
one, and then it's -1.
Two
Yeah, but
lines.
Oh, look at this!
It's
You're
like
even
this.
drawing your
it's
stuff.
like
I've already
It looks
started
like this.
drawing.
Yes.
I've already
This is
started
a-
drawing.
This is a red line. This is a blue.
Oh, look at you.
Yeah. And this one's a closed circle and this one's an open circle.
Carson's doing like, yeah.
I think Carson's broken back there. Okay,
That's the new dance move.
so this first piece, greater than or equal, so when you plug in 0, that would be a closed circle, and you get out 1, and it's for everything larger than
Oh.
0, so we're just getting this horizontal line at 1. Second one, you're getting a horizontal line at -1, but would it be open or closed?
Open.
Open because there's no equal to. Now, if you
Oh,
needed
she's
to,
color coded it to my vision.
I did, I had to match your vision.
Oh my
That
gosh.
is perfect. That's exactly what I saw.
So, if you didn't just have this beautiful picture in your head, what would you have done to graph this?
Just do the points.
Make a T-chart? Like, isn't that how we graph our piecewise functions? T-chart for each piece? So where is this discontinuous at?
0.
Oh, 0, yeah.
Because the function and the limit don't equal each
Don't
other.
have it.
Yeah, you could tell me, does the function exist?
Yes, there's the
Yes. Does the limit exist?
point. Oh, no.
No. So there is no limit, so therefore it doesn't equal the function either. But limit does not exist.
I like that it's just a graph. Well, if it's discontinuous, couldn't you always say rule 3 because they whatever?
I want the best.
Do you want us to say like 1, 2, 3, or just?
I would just, I mean, you could if you really wanted to, but I figure by the time it comes to test, you won't really remember what order they came in, so just tell me in general. Limit doesn't exist, function doesn't exist. Or
What
limit
is
doesn't
happening?
exist. So if we look so far, we had a graph with some things. What about this function made it not continuous?
Then at the bottom of 0.
Okay, the place with the bottom of 0. When was this one not continuous?
0 because they didn't equal each other.
Okay, so we had a piecewise in our breaking point that was discontinuous.
Yep.
All right, so let's kind of go through some different functions and see if we can find their discontinuity.
I'm
What?
just saying, I'm
You've got these beautiful
cracks.
pictures in your head.
Yes. they're
Too
flying
many
at me.
pictures. Too many pictures.
Make it stop, make it
Shut up,
stop,
Carson.
make it stop.
Solve first.
Okay, can you just look at the equation of A and tell me where it won't?
Yeah, too.
Why? How'd you just know
The
that?
bottom will be
It's
0.
Because there's going to be a hole at x minus 2.
So I wanted to know where was the function discontinuous? So A at x equals 2. The reason?
The function does not exist.
Mhm. So if we have a fraction, do we even have to draw the graph? No. You know, anything that makes the denominator 0 has to be a discontinuity on our graph. B. Alright, this is a piecewise. So we get 1 over x squared if x does not equal 0. And we get 1 if x does equal 0. Right, that's a little harder. If I just gave you 1 over x squared, where is that not continuous?
At 0.
At 0. But then I gave you another rule for 0, didn't I?
Yeah.
Okay, so where are we concerned that it might not exist?
0.
0. Let's kind of look at our graph.
So we just.
So I can't put in a 0. 1 over 1 squared is 1. 1 over 2 squared is 1/4. 1 over 1/2 squared would be 4. 1 over -1 squared would be 1. 1 over -2 squared would be 1/4. So it looks like this, which I'm sure is that picture you had in your head.
It is
Yeah.
spot on.
Spot
I
on.
did not have a picture.
I don't know. Mine was a little bit more curved.
And then 1 if x equals 0. What's that?
Just
A line.
It's a line?
Or a dot.
A dot. When x is 0, we get out 1. Okay. So we were worried about 0. Does the function exist at 0? Yes. Does the limit exist at 0?
Yes.
It
But they
does.
don't match.
Oh.
What does the limit go to as I'm approaching 0?
Infinity.
Infinity. The function exists, the limit exists. Do they match?
No.
No. So my discontinuity is at 0 because the function doesn't equal the limit.
Did we apply the same theory for C
Okay, so C, where do we think it may not work?
too?
2. Let's check.
Hmm.
Plug in 1, it's 1 minus 1
Okay, what does,
minus
so we have a point at 1, 2. Would everybody agree with that? So, or sorry, not 1, 2, 2, 1. When x is 2, y is 1. Okay, this other, we have to look at that a little bit closer. The top would factor into x minus 2, x plus 1. The bottom is x minus 2. What happens?
That's with the whole,
Yes, look at you remembering.
oh yeah.
So that means there is a hole in the graph. At 2, comma
3.
3, if you plug 2 into the final equation. So 2, 3.
Is there a hole because it does not equal to?
Yes.
Why there's no? Okay. I didn't know if that was because we canceled something out or.
That happens when they cancel. That's why we didn't have a vertical asymptote, we had a hole.
So it's
2,
gonna be
because that's what makes x minus 2 equal 0. 3, if you plug 2 into the final equation. Because this is just a line, y-intercept of 1, slope 1. So we have a line with a nice hole in the middle. So, does the function exist at 2?
Yes.
Does the limit exist at 2?
No. Yes.
Yes.
Yes, 'cause
What's
it
the
doesn't
limit
go
going
up.
to?
Infinity.
No. The limit as x approaches 2 is,
Infinity.
3.
Oh, 3.
if I am on this line approaching when x is 2, my y is going to 3.
3.
So the function is equal to 2, or to 1, the limit is equal to 3.
So function does not equal 1.
So it was at x equals 2, which is what we predicted. So are we getting a feel for things that make it not continuous?
Oh.
That's kind of our goal right now, just looking at where we have problems.
What do the fun brackets mean?
Greatest integer.
Well, that's
Yeah.
not continuous at all.
It is not continuous. So the greatest integer function, remember our step function, you put in 0, you get out 0, it's on, up until 1, you're still getting out 0, and then it ends with an open circle. Remember this? So where does this not exist? Or where is it not continuous?
At all
All
whole
integers.
numbers.
So discontinuous at all integers. Does a function exist there? Yeah, does a limit exist?
Kind of. Some places.
One-sided, but from both sides?
No. Unless it's in the middle.
But that, we're talking about where it's not continuous. So at the
Yeah.
integers, it's not continuous
Yeah.
because the limit doesn't exist. Alright. So I want to go back and talk about some of these. We have different types of discontinuity. C. That one's a special type. It's called removable. Because if this second point had been 3 when x equals 2, that would have moved my point to here. Then would it have been continuous?
Yeah.
Yes. So in part C, that is removable because we could fix it at that number 2. Same thing with part A. We didn't draw that full graph, but it's the same one, just without the dot. So if it's just an open circle on your graph, that's the problem, that's removable. If we think back to that first picture I gave you. At 1, this would be a removable discontinuity. I could fix it if I just filled in that dot. The second type of discontinuity is an infinite. You have an infinite discontinuity when something's going to infinity. So when your limit is going to infinity. So if we look back on part B, the limit was going to infinity. What causes our limit to go to infinity?
The fraction.
Yeah, when we have those vertical asymptotes. So vertical asymptotes, those are going to create infinite discontinuities. The final type is what we're seeing like on part D, where you jump from one step to another. That is called a jump discontinuity. A lot of times those happen in piecewise, but not always, because we saw a piecewise function where it was infinite. We saw one where it's filled in, but a lot of times that occurs. So if we looked at this one, what type of discontinuity is at 3?
That is.
Jump, because you jump from one piece to the next. What type of discontinuity is at 5? The removable, because I could have fixed it. Alright, so those are the 3 types. That's probably another slide that you should put a big star next to. Removable, infinite, and jump. Sometimes I will ask you to find and classify your discontinuities. So if I ask you to classify, it's one of those words. Alright. It's possible to be continuous from the left or the right, so kind of like when we talked about our greatest integer. Okay, if I'm on a particular piece, let's say I'm right here, when x is 1. Okay, as I'm approaching 1 from the right, if I'm coming in bigger than 1, my function's defined. Does my limit exist as I'm approaching from the right?
Yeah.
Yeah. Are they equal as I'm approaching from the right?
Yeah.
Yes. If I'm approaching from the left, are they?
No.
No. So it's possible to be from the left or the right if we were asked to define it that way. All right, so now we're just going to practice. Where are things continuous or not?
Everywhere.
Why?
Because it's polynomial.
If you recognize that, I am not going to make you show me a whole lot of work. This is a polynomial. We know every polynomial is continuous. So if you recognize a polynomial, you can just say, that function is continuous. All right. Let's look at the next one. All right, where would we be worried about this one?
5/3.
Why?
Because that's where
Makes it
0
zero.
is for the whole, or the asymptote.
So it's really kind of like finding domain, isn't it? So x cannot be 5/3. So if I said where is it continuous, that's everywhere except 5/3. So negative infinity to 5/3, union 5/3 to infinity.
I did write an 8 instead of being inside. Was that good for me? Like completely vertical, like not even,
Oh, wow.
not even tilted. Just a
It's a little
negative,
bit
just a negative 8.
If I asked you why is it not continuous at 5/3? Which rule of this rule of continuity does it break?
The limit, or the function limit.
Yeah, the function does not exist there because it makes the denominator 0. To check if it was removable or infinite, what we'd really have to do is just try to factor the top. If it canceled out, that's removable. That's a hole in our graph. If they don't cancel, it's infinite. We have a vertical asymptote. Would this one cancel?
No,
No. So what type of discontinuity would it be?
the first one.
It would be removable is a hole.
No.
That happens when things cancel. So if they don't cancel, no,
Infinite.
it's infinite.
Because it goes
it's
up
a
and-
vertical asymptote there. All right. What would I have to do for this one?
See if it factors.
Okay. We need to try to break down the denominator because we know in a fraction the denominator can't be 0. Is there anything that multiplies to 5 and adds to 2?
No.
No? Okay. Why don't you guys graph x squared plus 2x plus 5? Look at that graph for me.
Let me get it in my brain.
Stop
He's
on.
got this.
There,
Finland is not getting comfortable.
of course not.
We gotta calculate it.
Yeah.
That's exactly what you want.
Is it good for me that it's not showing me at all?
Hit zoom 6.
Is it 6?
So let me subtract 1, so it's up 4.
I did 9 like a fool.
So it's like
I
a
think it's just
parabola moved
parabola.
up 4. Yeah. That's all it is.
Parabola, right? Does that thing ever hit 0?
No?
No.
No. If you did the quadratic formula, you would have gotten an imaginary number. So if the denominator is not 0, where is this continuous?
Everywhere.
Everywhere. So it's okay have a fraction, sometimes if the denominator can't be 0, it's still continuous.
So two.
Wait, so is it just continuous everywhere just because it doesn't hit 0 at all?
Exactly. Alright, x minus 1 over x squared minus 4. So we know in a fraction, the denominator can't be 0.
Give me positive or negative.
Yeah.
So it's continuous everywhere except those points, or you could say everything smaller than -2, everything between -2 and 2, and everything bigger than 2.
Where'd that trash can go?
It's over here. There's still one in the front.
So like 2 and 1, so.
Okay, let's look at another one. Find the points where this is discontinuous and decide if it's removed. Okay, so let's just start. I'm going to go ahead and keep this in a fraction since I'm trying to check if it's removable. If I factor the denominator, what does that turn into?
X minus 2, x minus 1. It is removable.
What happens right here?
There's a hole.
They cancel it, so there's
So
Those
it's 1
cancel.
over x minus 1.
Okay, so this is discontinuous at what points?
2
X equals 2 and x equals 1. Because both of those make the denominator 0.
Oh.
Anytime something cancels like this, that is removable. So x equals 2 is a removable discontinuity. It makes a hole in the graph. If you're left with something on the bottom that doesn't cancel, what that means is it's a vertical asymptote. So a vertical asymptote, that is
infinite.
infinite.
You said this earlier, maybe I didn't understand. When we got that point that was 2, 3, was that because it was x minus 2 and that canceled, and then the bottom it'll be x minus 3? Is that, okay, I just wasn't.
Oh, it was because the 3 came from,
Let me put.
if you plug, we were left with x plus 1, so you put a 2 in it.
Oh, I'm putting the 2 in there.
You're finding out what this point would have been if it had dropped out of the graph. So, okay, if I asked you how I would fix this, we said it's removable. If I wanted to fix it, we would just have to make, or let's say, add the point. So it's basically filling in the hole on the graph. So the x would be 2. If you wanted the y value, you plug 2 into your final equation. So if you put a 2 in here, what would you get? 1. So your original graph will have an open circle at the point 2, 1. So if you wanted to fix that, you would have to close in that circle at 2, 1.
I got that right, but I don't know how I did that before you said that.
Oh, you
And I
did?
don't know how I got there, I don't remember what process I did.
That's funny.
It's not clear why I did it.
Let's look at another one. All right. So I have the absolute value of x minus 1 over x minus 1 cubed.
Can we make those maybe cancel a little bit?
Okay.
It's good.
Anytime we have absolute values, what do I make you do?
Piecewise.
And we do our two separate things, right? We rewrite it without absolute values. Our breaking point
Right now.
is what makes x minus 1 equal 0? 1. So we have to have a piece when x is greater than 1. We have to have a piece when x is less than 1. Can we have a piece where x equals 1? Why?
Bottom, give me
If
1.
it
Bottom.
equals 1, then not work.
Okay. So if x is greater than 1, if you put in a number bigger than 1,
It's gonna be 1 less than
Okay,
It'd
so
be
it's positive. So does the absolute value change it?
No.
So you get x minus 1 over x minus 1 cubed. What would happen?
You cancel out, you get 1 over x minus 1 squared.
If you put in a number smaller than 1, then the absolute value, the number inside would be negative.
And then become positive.
So it's the opposite of x minus 1. So if you cancel an x minus 1, you'd be left with negative 1 over x minus 1 squared. Now, was this really necessary? Maybe not. But I told you, with a piecewise function, where should we be concerned?
The piece that doesn't, where it's trying to get you to solve to.
Where it breaks, right? If we could look at a graph here, we can talk through it, a lot of different things. We already know 1 is a problem because can you plug in 1?
No.
No. So it's discontinuous at x equals 1. For several reasons. You can't plug in 1, so the function doesn't exist. If you were approaching 1, these pieces don't match. If you did go ahead and graph it, when you're coming in greater than 1, it's going to look like this. When you did less than 1, it's going to look like this. So the limit doesn't exist, the function doesn't exist, it breaks a lot of
So
rules.
how do we decide the 1 over x1 squared and the negative 1 over x1 squared? Like,
We talked about what the absolute value would do. If your number is bigger than 1, when you subtract 1, it's still positive, so the absolute value doesn't change it. And then we cancel the x minus 1.
Looks to me
If you put in a number smaller than 1, it's negative, and the absolute value does the opposite, to make it positive.
on these notes, it looks like you edited these today before you print them. Never mind, today's not the 5th.
What type of discontinuity is
Infinite.
this? Infinite. Because we have a vertical asymptote at 1. Since the 1 makes the bottom 0 and it doesn't cancel out entirely, then it's a vertical asymptote. Alright, we're going to do one more on this. I want to find a to make this function continuous. If it is continuous, what does that mean?
Never picks up the
Never picks up the pencil. So you'll notice I have a piece when x is less than 1 and a piece when x is greater than or equal to 1. So 1 is my breaking point, right? 1 would be the place where I would jump from one piece to the next. If I don't want to jump, what has to happen when x equals 1?
Has to hit whatever that.
We have to equal.
They have to equal, right? When I graph my piecewise, those pieces have to match up. So we need to set these equal. But they don't always have to be equal. They just have to be equal at what point?
1.
When x is 1. So now we plug in a 1 for our x. So 1 squared is 1, minus 2 is negative 1, equals a minus 4. A is 3. So if you want to make a piecewise continuous, your pieces have to match. Okay, we're going to do a handout together, or part of it. Together.
Together. Together.
If we look at number 1, I want to know where is this function continuous. So without checking anything, where would you be worried about it not being continuous?
1.
1. What would make it continuous at 1?
If there was an open circle combined with the closed circle.
Okay, if they were equal at that point, right? Can we quickly check if they match up at 1?
Yeah.
Yeah, this one would be the point 1, 0. If you plug a 1 into this one, what do you get out?
1.5.
1.5. So do they match up? Are the y's the same?
No.
No. So you could draw a whole graph, but you don't have to. We already kind of know what would make it a problem. The only way it would work is if 1 was the same. It's not. So I'm asking, where is it continuous?
Negative theta 1, union 1, union 3.
Number 2. We have a negative x squared over 2 plus 1. What do you think?
Negative infinity, 2 infinity.
Yeah, that would be the same as if I wrote negative 1/2 x squared plus 1. That's a polynomial. Polynomials are continuous everywhere.
If you start seeing random 8s on my paper, no, you are not. They are infinities.
Okay, number 3. Where do we need to be worried?
At 3.
0 and 3.
Okay,
Oh,
so
0.
if we factor the bottom, we could take out an x. Anything that makes the bottom 0 is going to be what?
Asymptote.
So I know that x can't be 0 or 3. So it's continuous everywhere else. What would that be as an interval?
Negative theta 0, union 0 to 3, union 3 to 0. Or 3 to 3. I don't know why I thought that that point could work.
Everything smaller than 0, between 0 and 3, and bigger than 3. Number 4. Where do we need to be concerned?
1.
Why?
Because it doesn't equal.
Okay, because that is the breaking point between these two pieces. We have one not equal to 1 and one that's equal to 1. So what we need to do is plug a 1 in and see if by chance these pieces match up. If you plug 1 into the top, what do you get?
2.
And if the bottom, we get,
Negative 2.
so do they match up?
No.
So it's not continuous at 1. So my answer is,
Negative theta 1, union 1, infinity.
all right. Do you guys feel like you could handle those types of problems if I gave them to you?
Yeah.
Okay.
The wording on this next section is kind of.
So the next section says determine if the function is continuous. If it's not, find the x-axis location and classify each discontinuity. So it's basically the same thing, but I want you to tell me what kind of discontinuity it is. So here we're basically finding where it's not continuous. Okay, so where is this going to be discontinuous? Can you tell me?
Negative 2.
So discontinuous at x equals negative 2. To classify it, we need to go back to our function. The top would factor into x plus 2, x minus 2. The bottom is just x plus 2. What would happen?
It removes.
Yes. So the type is removable. Anytime the discontinuity would cancel out, that's removable. Creates a hole in our graph.
2, 0.
Yeah. If you were actually finding the point, yes.
This is fine.
It said.
Find the
x-axis location, so x equals 2.
Oh, is that what it is?
But if we wanted to fix it, it would be negative 2, comma, negative 4. I think you plugged
Do
in
we have
positive
to
2.
fix it on this?
It didn't ask for you to fix it. All right. Number 6. So we have our function. 0 when x is less than or equal to 1. Negative x over 2 plus 3 halves when x is greater than 1. Where should we be concerned?
At 1.
At 1. So let's check. The first one, if you plug in 1, you get out 0. Second one, if you put in 1, you get out 1. So definitely discontinuous at x equals 1. What type?
So it's not removable.
Not removable because it didn't cancel.
It's not
It's
infinite.
a jump.
It's a jump. Oh.
Because you jump from one piece to the next. We had one piece for everything bigger than 1, one for everything less than 1. So we are jumping. on this one? Factor. So multiply a -3, add to +2.
Positive 3, -1.
Nothing cancels out. Where is this discontinuous?
1 and -3.
Or -3, close.
Okay, neither one of them canceled, so what type are both of them?
Jump.
Yes.
Infinite.
Yes.
Oh, shoot, dog.
Okay, remember, when do we get a removable?
If they
They
cancel out, so if they
cancel.
don't cancel out, it's gotta be infinite.
Right. Removable is when you factor and it cancels. If they don't, it's on the bottom, it's a vertical asymptote. When you approach asymptotes, you're going to infinity, so that's an infinite.
Oh, genius.
Alright. We've got a couple more minutes, let's try to do.
What did you say?
Where should we be concerned?
-2.
So, if you put a -2 into the top, you get 4 minus 12 plus 9. So that's 1. The bottom is -2, 0, so they don't match. It's discontinuous
It's a jump.
at -2. Now, we have to be careful. You are on the first piece when?
Oh, it's not a jump, no.
When are we on this first piece?
Cross country is dismissed at this time. Cross country is dismissed at this time.
Anything except -2. So what that does
Make
is
it removable?
it's an open circle, yes. So this one is removable. You can graph, that is a great option. What I would watch for, the removable happens when something cancels in top and bottom, or when you have a piecewise and your conditions are equal and not equal. Because I knew then, because this one was not equal to -2, the only difference was a single point. Versus when you have a piecewise where your conditions are greater than and less than, that's when you jump, because you start on one piece and then you actually jump to a different one to continue. So that not equal is what made this one removable.
Mine's got me a little confused.
Oh, nah, I'm cooking on that.
Because you get rid of that X, but then you don't know what it's gonna be.
So
Yeah,
if we
it's
look
removable.
at number 9, we have -x over x squared plus 3x. So if we factor,
Oh, it's just that.
the x comes out, x plus 3. So if you cancel the x, that just leaves a -1 on top. So, give me a second. So when we look at our discontinuities, there are 2. Anything that made the bottom 0. So what makes just a plain x equal 0?
Or, yeah,
So at x equals 0 and at
-3.
-3. Now when I'm classifying, the 0 canceled. If it canceled, that made a hole in the graph, so that is
Movable.
removable.
Yeah.
If it doesn't cancel, we know it's an asymptote.
Infinite.
That is
Wait, how do we get x equals 0?
when you had this x.
Oh, wait, before we get to that.
Mm.
Oh, you gotta factor it, huh?
Last problem for the day. What makes the bottom 0?
One.
So it is discontinuous at 1. What type would it be?
Infinite.
It would be infinite because we're in class.